many months do you think you spent on trig last year? You started in like January, because I know you started it right after Christmas. You learned the unit circle, and then you learned maybe some trig, like some SOHCAHTOA triangles, and then graphing. 2 months? 3 months? Okay, well, we're just going to cherry pick some of those things that you need. Like, you're not going to need the law of sines and cosines for calculus. You're not going to need a bunch of identities for calculus. We're just going to cherry pick a few things, and we're going to do it in 2 days. All right? So please stop me if I make a statement that sounds like I'm assuming that you remember something, because if you got to let me know, because last year was like a total blow up, right? I don't know how much you remember from last year. You never took a final, so you haven't thought about trig since, February. So let me know if I make something and you're like, wait a minute, I don't remember what you're talking about. Okay, so just stop me. All right, but you're in good hands, and we'll get through this together. Okay, so let's talk about what we're going to talk about today, 6A. We're going to talk about radian measure. Okay, so that's measuring things in pi instead of degrees. So we're going to talk about that. We're going to talk about the different sinusoids. A sinusoid is just a trig graph. Okay, it's amplitude, period, waves. Okay, a sinusoid is anything that's wave or repetitive. So we'll talk about that. And then we'll talk about how to move those graphs side to side and up and down and reflect them like you do with a parabola or anything else. Okay, so those are our goals for today, what we'll get through. So let's start with radian. So in calculus, we pretty much don't use degrees anymore. Right? If you happen to be taking physics this year, physics pretty much does everything in degrees, and calculus pretty much does everything in radians. So is there anybody who is in physics right now? Okay, so you will probably need to be switching your calculator modes back and forth depending on what assignment you're working on, all right? And I will try my best to remember to remind you, especially before a test or quiz, like, hey, radian mode, be in radian mode, because you don't want to be in degree mode, okay? All right, so let's review how we measure a circle in degrees. So one of the first pairings, okay, like for example, 60 degrees. That's a third of a pi, okay? 1/3 pi, or pi over 3. So full circle being how much? 2 pi, right. Half circle being 1 pi. 90 degrees? Pi over 2. 45 degrees? Pi over 4, the biggies, okay? We're not going to get into like pi over 7, okay? We're going to stick with nice radians. Okay, so what is a radian? Okay, it is a portion of a circle, and the circle has radius 1. We measure the outside of well, what's the outside of a circle called? It's circumference. What's the formula for a circumference? 2 pi r. But if the radius is 1, then the outside of the circle is 2 pi, which is why we measure a full circle in radians of 2 pi. Okay, so all the way around is the same as measuring the circumference. And so every time you cut that up, you're taking a fraction of that. You're taking a portion of the 2 pi all the way around. So when you are taking half of it, it's half of 2 pi, which is pi. It's half a circle. If you're taking a quarter of it, it's a quarter of 2 pi, which works out to be pi over 2. Everything's based on 2 pi. We place our circles in such a way that we measure 0 starting with the x-axis. So 0 is always set right here. We call that 0 pi. It's not 0 degrees anymore. It's 0 pi. And then we measure what's called counterclockwise. So we measure up into quadrant 1 and then around. Is it possible to go all the way around and then continue? Yep. For sure. Okay, then you're just going to go past. Those are called coterminal angles, and you go. We mostly are going to stick within 0 to 2 pi. But you should be comfortable if I ask you, well, where's 3 pi? Right, so well, 3 pi is if I went all the way around and then went around again and stopped right there as an example. Okay. So let's just practice how we go back and forth between the different, from radians to degrees and back and forth from degrees to radians. Okay, you'll need the conversion ratio. So we say that radians to degrees, so R over D, is always done with the conversion ratio of 1 pi over 180 degrees. So you take anything equivalent. Now you could do this with 2 pi and 360. You could do it with a half a pi and 90 degrees. You could do it with anything. We just find the math works out best when you use 1 pi and 180. So you're going to use that as your conversion factor, and you'll cross multiply to solve anything you need to convert. So let's do just 4 quick examples. So number 1. Let's convert pi fifths. All right, so when we want to convert pi fifths, we'll drop pi fifths into the top of the ratio, because that's where the radians go, and degrees is on the bottom. Then that's equal to pi over 180. So some of you can do that in your head. Others of you need to, see the mechanics of working it out, but we cross multiply. All right, when we cross multiply, we get 36 pi equals pi d. And so if you want to know how many degrees it is, divide both sides by pi. And the pi's reduce away. So this is a 36 degree angle. Yeah?
Could we not, like the way we learned it in hand, is that you take like pi over 5 and you multiply it by like 180 over 5?
You're multiplying by the reciprocal.
Right.
Yep, that essentially does the exact same thing.
Okay, so we could do that way.
Sure. If you want to go from radians to degrees, you multiply by pi over 180. If you go from degrees to radians, you multiply by 180 over pi. Yep, that'll totally work. All right, number 2. All right, so convert 27 degrees. All right, so then R would be on top and 27 would be on the bottom, being equal to pi over 180. You cross multiply that. So basically, Meg, to answer your question, this is why what you're saying works. It works because it's coming from, you're just skipping you're going right to the, you're skipping the cross multiplication step and going right to it. All right, so R times 180 equals 27 times pi. And then you divide by 180. So the radians would be 27 degrees over 180 degrees pi. And the degree symbol reduces because units reduce, just like anything else. And then 27 and 180 are both divisible by 9. So you get 9 over 20 pi. And that's not reducible anymore. So you do need to put things in lowest terms. Please don't ever turn it, what did I do wrong? Oh yeah, thanks. Don't use decimals, please. Okay? Don't turn 3 over 20th times pi into an irrational decimal. Because as soon as you use a decimal, you have to round it. And because it has infinitely many of the decimals. And as soon as you round it, you've lost accuracy. So the more accurate would be to write the fraction times pi. So please always leave it in its most accurate form. All right, any questions about, we don't need to do 4 examples of those. I think 2 is fine. Any other questions about that? Okay. Okay, here's where you may be a little bit more rusty on the different graphs of trig functions. Okay, I do not expect perfect graphs, but general shapes. Okay, sine and cosine have the same shape, they just start differently. You need to be very comfortable with the fact that sine starts at the origin and cosine does not. Be very, very clear in your mind about which one does that. Otherwise, they have the same shape. Their rules for amplitude are the same. Their rules for period are the same. It's just that their starting point is different. So make sure that sign starts at the origin. Sine is an odd function. Odd functions start with the letter O. Odd functions have to go through the origin, which also starts with the letter O. Okay, odd functions go through the origin. Sine has to go through the origin. Cosine is an even function. Even functions have to be equally symmetric over the y-axis. You should be able to take the y-axis and fold it, and that's an equal, even symmetry. Tangent is also an odd function, so tangent also has to go through the origin. So sine and tangent are both odd functions, and they both go through the origin. All right, then you've got cotangent, which looks a lot like tangent, but does not go through the origin, and it's a decreasing instead of increasing function. So I'm just going to go, we're going to come back to this one in just a second, but okay, look at cotangent, which is right below it over there. Cotangent does not go through the origin. It has asymptotes, but it's decreasing. And then we're going to talk about the best way I know to graph sine and cosine in just a minute. Well, let me show you something on here. Okay, secant has an invisible cosine in it. Secant and cosine are partner, are reciprocal functions of each other. And there is a cosine graph that fits in between a secant graph. They all touch at all the important points right there. The maxes and the mins all touch. So a secant has to be the reciprocal of cosine. And then next to it, cosecant, you have a sine function that goes through the origin and touches all the peaks of the other one. So for me, I usually try and remember that cosecant is paired with sine, that they are reciprocals of each other. So I usually sketch a little baby sine graph first, and then I make sure that my cosecant graph goes off of the peaks and valleys of my sine graph. And for the other one, I'll graph a cosine first, and then I'll make sure my peaks and valleys go off of that. That's one way I use to keep them straight. So we're going to practice our graphing. Now, I put some graph paper right into the notes, so you don't have to go over to that other handout. But we're going to talk about domain, we're going to talk about range, and we're going to talk about amplitude and period. Okay, sine and cosine are the only two that both have a domain of all real numbers. So I want you to look at both of these have a domain of all real numbers. So it goes to both of them. So why is that? All right, well, let's go back to our rules for domain from last week. What kinds of functions are the ones that have restrictions? Functions that have what? Square roots. Okay, sine and cosine clearly don't have a square root. What else? Denominators. Do sine and cosine have denominators? No, they're the only trig functions that don't. All the other trig functions have denominators. What's tangent's denominator? Cosine, right? Because tangent is sine over cosine. And cotangent's denominator is sine. And they have denominators so that they're not all real numbers anymore. And secant and cosecant, they both have denominators. Cosine and sine are the only two functions that don't have denominators. Therefore, they're the only two functions that their domain is all real numbers. All right, now their ranges are depending on the amplitude. The ones that are drawn for you, the amplitude is 1. So the range for both of them is -1 and +1. But if the amplitude is stretched taller, that'll affect your amplitude, your range as well. But the other ones go forever. So they've got infinity, tangent, cotangent, have all real numbers for their domain, for their range, because they are infinitely low and infinitely high. Okay, any questions about that? All right, so we're going to talk about how do we come up with domains for the other ones? If the other ones have denominators, how are we going to come up with what the domain is then if it's not all real numbers? But let's talk about sine and cosine first. Okay. When you make a graph, there are a couple key points to look at. That front value of A determines your amplitude. If there is a coefficient in front of X, that determines your period. And the period comes from the equation 2 pi, which is a full circumference of a circle, divided by B. Okay, 2 pi divided by B. And then we can move these things side to side and up and down. Now, Esther, I don't think you realized what I was going to do today, but I have my own slinky for a little demonstration. Mine is in better shape than yours. Okay. All right. So, if you look at this slinky straight on, what shape do you see? Okay. Can you tell how many circles there are in this slinky? How would you tell how many circles there are? Well, you got to turn it sideways. And then what do you got to do? Stretch it out. And when you stretch it and you look at it, if I can stretch it far enough, this is a sine graph. Okay, it's a sine wave. It has an amplitude, up, down, up, down. If you could see this all the way straight, it's up and down and up and down. It's a perfect sine graph. That's the relationship between a unit circle. That's why the circumference of a circle is 2 pi. But if we want to know the period, we got to turn it sideways and we have to take 2 pi and we have to spread it out and divide it by B so we can figure out the period of one of them. Because B is how many of these cycles there are. And then you can measure the period of one. All right, that's the forwards, or the front view and the sideways view of, that's how a unit circle turns into a wave. You're looking at the unit circle sideways. Okay. All right, so let's practice this a second. Determine the period, domain and range, and draw the graph. So we want to kind of diagnose this as we go. All right, so period. The period of this function is the 2 pi circumference divided by what number here? 4. Okay, the 4 is that coefficient there, so my period is pi over 2. All right, the domain. Well, this is a sine graph, so the domain would be automatically all real numbers because sine doesn't have a denominator. The range of this has a lowest value to a highest value. All right, what is the lowest value of this? What's it going to dip down to? 2 is not the lowest. The lowest is -2. And then the highest is +2. Okay, so this is going to be fluctuating between, and we can tell that because of that 2 right there. So the lowest to the highest would be -2 to +2. So you can write that in interval or in inequality notation. So you can say -2 less than or equal to y less than or equal to 2, or you can write it with brackets -2 to 2. Doesn't matter to me. I will usually write it as inequality. So it's up to you. Okay, now to draw the graph, we're going to go to our graph paper, which is on the next slide. So I made you some space. Now notice that the question changed a little bit from the previous slide till now. So can you tell the difference? Okay, Meg, what do you notice different? It is factored in factored form. So the question was given to you in distributed form, 4x plus pi. In order to accurately graph it, it has to be in factored form. So you need to divide both these terms by 4, which is what factoring is, it's division. Put the 4 outside and put what's left in the inside. All right, make sure you do that before you graph it. If you try because otherwise your translation to the left or right will be off. All right, so here's how I'd like you to draw your graph. Draw a wave first and then label it later. Sometimes I have to break you of a bad habit, and you try and label your axis first, and then you try and squeeze your graph into your labels. I'm going to suggest draw your graph first and label it later. Okay? So draw your graph with enough space. Start at the origin. It's a sine graph. Now I do know that it's an upside down sine graph because of the negative. So I would encourage you, I usually skip every about 2 marks, and I'll go and I'll put my, I'll do about every 2 hash marks, and that gives me enough space. So I use 5 dots, and then I play connect the dots. So I start at the origin, I go down, ooh, not so good, try again. Go down, connect the dots, go up back through the axis, connect the dot at the peak, and then come back down again. So, oh man, I missed it again, out of practice. Try there, that's better. Okay, 1 cycle is good. You don't have to do, okay. So draw it first, and then go and put your labels on. So we knew that the amplitude, the range of this is supposed to dip down to -2 and up to +2. So I'm going to label my y-axis with my amplitude. I know that my period is supposed to be pi/2 from the previous slide. So I label the origin as 0, and I label the end of the first cycle at pi/2. If that's the end of the first cycle, then the center of the cycle has to be pi/4. Draw it, then label it, and then move it if you need to. So then I'm going to look back at this, and I'm going to notice that since I wrote it in factored form, it's going to move to the left, the equivalent of pi/4 units. So I'm going to use, you guys are in Notability. I'm not in Notability, and I'm in a different app now. But if I were, I would use my Notability, and I would just cut out that thing, and slide it over. I'm going to draw it in a different color right now, but I move it to the left, pi/4, which on my scale is worth 4 tick marks. So I'm going to go to the left, pi/4. So everything will move over, and my graph will look like this, which looks like a normal sine graph, which is back to going through the origin. So you might be asked, now write an equation, a simpler equation, that would represent the blue graph. Okay, a simpler equation, well, it still has the same amplitude and it still has the same period, but it has a different translation. It's not reflected anymore, and it's going right through the origin. So I could also write this as y equals +2 with no reflection, sine of 4x with no translation. So no reflection, no translation. So the original graph and this one are the same. Those are equivalent. Okay, now what if I ask you to turn this into a cosecant? So I'm going to erase my red graph just so I have a little bit more space to write with. I don't need that anymore. All right, how would I turn this into a cosecant?
Did you just draw like these touching the maximum and
First I'd draw asymptotes, but then I would draw the u's. Yeah, so first I would draw asymptotes. So I use my highlighter, and an asymptote is going to come through every place that this graph touches the x-axis. And so I'm going to have an asymptote that comes down here through pi/4, and I'm going to have another asymptote that comes right down the y-axis, and I'm going to have another asymptote that comes right down everywhere where it has an x-intercept. So why is that? Okay, well, what's the value of an x-intercept? 0. I'm drawing a reciprocal. So what's the reciprocal of 0? No, the reciprocal of 0 is not possible to be 0. Okay? Why? Because what's under 0? Okay, this is equal to 0. Okay, there's a 1 under that 0. There's a 1 number under every number. So what's the reciprocal of that? 1 over 0. And what's that equal to? That's equal to undefined. That's why every 0 on the x-axis turns into an asymptote, because an asymptote is the visual representation of undefined. We can't draw undefined, we draw it as an asymptote. That's the visual representation. And then I'll take my peak numbers, oops, and I'll draw the upper branch, and I'll draw the lower branch. And now that has been turned into a cosecant. So I'm going to do my color coding here. And the red equation is now y equals 2 cosecant 4x. It has the same, what we call amplitude. It has the same period. It's just fit in between the asymptotes. So let's talk about what the domain is of this. How would you write the domain of a cosecant graph, and how would you write the range of a cosecant graph? All right, well, the domain has to do with where the asymptotes are. So the cosecant domain is x not equal to every place that there is going to be an asymptote. So how far apart are the asymptotes spread from each other? Pi over 4. Every pi over 4, there would be a new asymptote. If I were to keep the pattern going, there would be another asymptote spread out. There would be another one over here, pi halves, because the space between it is pi over 4. And another one would be over here. They would all consistently be pi over 4. So when you write your domain, you say x not equal to k pi over 4. That means every spacing between the asymptotes is a version of pi over 4. But the k represents that it just kind of keeps moving down the x-axis, both forward and backward. So figure out the space between your asymptotes, and that's how you write your domain. The range is written one range for the top and one range for the bottom. And again, I'm looking only at the red graph. It has an upper range for the upper branch, and it has a lower range for the lower branch. So my range is y is greater than or equal to the number 2. That's the upper branch. It touches the number 2. It's equal to the number 2, and then it's going up. And we have the lower branch, which is y is less than or equal to the number -2. And so that is now below. So we have its domain and its range. All right, any questions about that?
How do you know the space between the things?
The space between what?
Like,
The asymptotes?
yes.
Well, okay, I knew that one asymptote was here at 0, and the next asymptote was pi over 4. So the space is pi over 4.
How do you know the second point is pi over 4?
Okay, well, I knew this one is negative pi over 4, right? Because every 4 marks, count 1, 2, 3, that's worth, every 4 marks on my scale is worth pi over 4. And so then I do another one of those. And what's pi over 4 plus another pi over 4?
So it's the same for everything.
Same for everything, yeah, they're equally spaced. Okay, let's try another one. Okay, let's do cosine. Okay, so I suggest draw first, label second. Okay, I know what cosine looks like. I know that cosine starts up here at the top, and then I just do every 2 again, so I make my cosine, and I use 5 dots, and I keep them equally spaced. right? Up through here, down, back up. That's what cosine looks like. The pattern continues, but I keep mine equally spaced. I use 2 dots, 2 hash marks between every dot is what I keep my spacing at. If you wanted to do 4 marks or whatever you do, keep it consistent. Then I label. Okay, then I label. So I know that the amplitude is 2. So I have 2 and -2 on my y-axis. My period. My period is 2 pi, which is the circumference, divided by the fraction half. What does that work out to be? It works out to be 4 pi. Not? The 2 and the half don't reduce each other. It's 2 times the reciprocal, so that works out to be 4 pi. So that means the spacing here is 4 pi, but I also have a translation. So I can't just jump and label this 4 pi. That would not be accurate, because it has to be 4 pi from the origin, so that's not quite right. I gotta think about my translation first. So remember that this is not factored. So we need to factor this out. So I need to rewrite this, pull the half out, and then x plus, okay, how does this work? Okay. So this means my drawing has to get pulled 2 pi in what direction? To the left. All right, so let's figure out how we're going to label this. This is a little trick I use, okay? I make a similarly shaped sine graph right next to it like this, because I know sine starts at the origin. So I just kind of sketch it real quick. That's where 4 pi has to end up. 4 pi's got to be there. It has to be the end of a normal cycle. Then I'll erase that, my sketch was, but 4 pi has got to be right there. Okay, it's got to be where a normal cycle would end. So then 2 pi has to be here. And 0 pi has to be at the origin. And -2 pi, I don't like where I wrote that. -2 pi would be here. So if I want to pull my graph to -2 pi to the left, it's going to go this way to the left. Just 2 marks, and then I'll end up at -2 pi. Make sure that your period, the label of your period, is the end of one cycle. Yeah.
Would you move it to -2 pi, or would you move it 4 spaces to the left, so it's like you're moving it to the left?
Nope, I move it to -2 pi, the end of cosine, or the beginning of cosine, whatever you want to call it, that little spot. Oh, I see what you're saying. Yeah, from the origin. Yeah, I would move it 4 spaces from where it is. So it would look like, so this peak should move to be above 2 pi, like that. And then, so I'm going to have like this. This is where it ends up in its final resting spot, like that. That's been moved 2 pi to the left. And I can turn that one into what's the reciprocal function for this one? I could turn it into, if I wanted, secant. And I would make the asymptotes down through where it crossed the x-axis. By the way, where is this crossing the x-axis? The blue one. Is it k pi? If it was k pi, then it would be 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. Is it crossing at, it is crossing at 1 pi. I agree with you there. But is it also crossing at 2 pi? What's the spacing between it? What's the spacing between the places where it's crossing the x-axis? How far apart are those? They are 2 pi apart. So how do you write that? You write that as 1 pi is where an example, 1 pi where it starts, and then K is on the 2 pi because the 2 pi is the space between it. So you were right that there had to be a K somewhere. All right, the only one we didn't get to was tangent. Oh yeah, and this one was easy. Okay, so maybe okay, let's keep going with a tangent graph. All right, so we know that tangent graphs have to go through the origin. So I'm going to sketch this, and then I'm going to label it next. So let me start with a sketch of tangent. So tangent normally goes through the origin, and it has asymptotes on either side. So I'm going to have an asymptote that comes down through, and I'm going to put my asymptotes equally spaced on either side of the x-axis. So you could spread those out a little bit more if you wanted to, as long as they were equally spaced. And a normal tangent is going to come up through the origin, going from left to right, increasing and going up. All right, but this is a reflected tangent. It has a negative. So it's not going to be behaving that way. It's going to be going down from left to right. So let me erase what I just drew here. And let's come down that way. So here's my tangent coming down through the origin. And that's repeated over and over and over according to the period. So there would be another asymptote equally spread. Now, how do I know how far apart my asymptotes are? Well, count the distance or measure the distance between them. There are 4 tick marks between that. So my next asymptote has to be 4 tick marks, 1, 2, 3, 4. So my next asymptote would be here. Okay, and then I'd have another identical cycle coming down this way. All right, and then it would just kind of keep repeating itself. And you'll have another one that would be 4 tick marks away from that. So you'd have another one. And then you'd have another graph coming down, hitting the origin. All right, now how do we go about labeling this? And I know there's a +1. I will get to that in just a minute. So let me just erase. I don't need this little green mark anymore. Okay, how do we go about labeling this? Well, we want to do our equation. And the equation for tangent, its period is no longer 2 pi divided by b. It is only 1 pi divided by b. And so my period is pi divided by b. That's for tangent and cotangent. So this will be 1 pi divided by 1/3. In other words, 3 pi. So that's my period. So that means the measurement between all the asymptotes has to be 3 pi. The measurement between all of the x-intercepts has to be 3 pi. Everything continues to be 3 pi. All right, so the easiest one is to start with your origin, which is at 0. So the next repeating one has to be at 3 pi. Okay, they're equally spaced. And so then the next one has to be at 6 pi. And the next one after that would have to be at 9 pi, et cetera, et cetera. Okay, and then how do we find our labels for our asymptotes? Well, we got to measure what's between 0 and 3 pi. So that would be half of that. So 3 pi over 2. And this one would be negative 3 pi over 2. And those are equally spaced. Last thing I need to do is bump this whole thing up 1 because of the +1 here. So each of these branches or graphs is moved up 1 unit. It doesn't change the labeling. It doesn't change the asymptotes. It just changes the general shape of the graph just because it's one up, but it doesn't change anything else about our domain or range or anything. Okay, so let's talk about our domain. How do we write that? Domain has to be connected to the denominator. The denominator is connected to the asymptotes. My asymptotes are spread 3 pi apart. All of my asymptotes are 3 pi apart. All of my intercepts are 3 pi apart. So how do we write that? Okay, x not equal to, because it can't be equal to an asymptote. I always write my first asymptote. So my first asymptote was at negative 3 pi. And then after that, they are k 3 pi apart. That's the pattern. The first one is at negative 3/2 pi. And then after that, they are every 3 pi spaces, multiples of k. You could even write plus or minus because this goes both in the forward direction and I could go backwards because there's a whole bunch of asymptotes off to the left as well. That's the hardest part, is figuring out how to write your domain. So a good rule of thumb is label your first asymptote and then the k goes on the spread, the consistent over and over spread between those two. Range is easy because for all tangent and cotangent, it's negative infinity to positive infinity, or you could write that as all real numbers and that would be fine. So the hardest part is the domain, I think. I want to look back. I was gonna turn that into a secant graph, but we didn't in class, so that's fine. All right, so that's my domain. Okay, so last thing. What would the amplitude and period be if you were looking at a drawing like this? So it helps to know the window. So we're looking at -5 to 5. That means the end over here is -5 and +5, and then we know we've got -4 to +4. Okay, so let's look at, I'm gonna color code it, okay? Let's see. Let's look at this yellow one. All right, so for my yellow one, what would the domain be, the question, what is the amplitude? And what is the period? All right, well, my amplitude is 1 tall. Okay, I go for the highest peak, and so my amplitude is 1. Now the period's a little harder to figure out because my period my drawing that I sketched hasn't finished a complete cycle all the way yet. All right, I know it's a sine graph, but it hasn't finished. In order to finish, I would have to go off the graph and come out and finish over here. Kind of have a hunch about this because if the picture of the graph ends at 5, where do I think this ends up? All right, well, that's probably right around 6 or a little bit more than 6. And I'll tell you, give you kind of like the inside scoop here. If it looks like it's going to be around 6, it's probably at 2 pi because 2 pi is just a little bit more than 6. All right, how can I be sure about that? Well, look here at this point. That one looks like it's right around 3. Well, what other number is right around 3? Well, it's pi. And if it looks like it's going to be pi, if it looks like it's around 3, it's probably pi. And I won't mark you off if you say 3 instead of pi or pi instead of 3. So I'm going to say that the period for this is 2 pi. 1 full cycle has to get me all the way to 2 pi. All right, now let's look at the other one. The other one is a lot more compressed. So let me erase some of the things I did on my drawing here. I'm going to switch colors, and now I want to talk about, I'll make it green. Okay, so let's talk about this one. What are the period and the amplitude of that? Well, let me just draw one cycle. One cycle ends right about there. All right, well, the amplitude's pretty clear. The amplitude appears to be 2. All right, and what about the period? Where does it appear approximately to be crossing? Well, it's not 1, and it's not 2. Okay, 1 would be here. 2 would be there. It's looking like it's crossing right in between 1 and 2-ish, around 1.5. Okay, well, what is right around 1.5, 1.6-ish? Well, that's half of pi. And so again, if it's matching up, those decimals look like it's probably about right, then that's what the period is going to be. So we're going to say the period is here, half pi. All right, so just some rules of thumb. Half pi, approximately 3.5 to 3.6-ish. Excuse me, 1.5 to 1.6. Pi, okay, approximately 3.1 to 3.2. 2 pi, that's approximately 6.2 to 6.3, a little bit more than that. So if decimal-wise it looks like it's hitting in about those places, that's what they're intending. So maybe you should know what is 1/4 pi, and maybe you should know kind of approximately what that is, because it might actually be right around that number. That's what when they draw these digital graphs, they're intending it to be in a radian measure, okay? All right, it's okay if you struggle with this a little bit. Again, I'm not expecting you to get everything 100% right the first time. We'll continue to talk about this more tomorrow, and we've got all day Thursday to work on reviewing trig together. All right, this is the first time you've thought about trig in a long time, so don't worry if it's a little rusty. All right, I'll see you guys tomorrow.